Let's continue with this problem. To check the introduction of this problem, please view the previous video. But basically, what is given to us is a chloroform and acetone mixture, binary mixture, wherein we're being asked for the uh, partial molar volumes of the species, of the two species at a given concentration of 10 mole percent. And then we're also being asked for the pure species molar volumes and the partial molar volumes at infinite dilution. We're given the data for the problem, uh, the molar volume of the solution with respect to x2. All right, so we begin with, okay, hold on please. Let me just go to the slide. Okay, we begin with this equation. Uh, However, the problem is, okay, we're supposed to use this equation, but the problem is the figure that's given to us is in terms of x2, okay? Uh, but our equations are in terms of the x1. So we have to derive an equation similar to this one, okay, but in terms of the x2. We can still use the first part of this derivation. We began with the uh, summability equation. We derive the summability equation. However, by Gibbs-Duhem equation, we assume constant temperature and pressure. So the first two terms is 0. So that means the last two terms right here is equal to 0. Okay? Because we assume constant T and P. So dt and dP are 0. And then instead of replacing dx2 in our equation, we replace dx1 with negative dx2. Let's try that. Okay, going back to our whiteboard. Okay. Again, we're trying to derive an equation for the partial molar property, but this time in terms of dx2. So we begin with uh, the equation, my dm is m1 dx1 plus m2 bar dx2. And then we replace dx1. Okay, we replace the dx1 with negative dx2. Okay, so we substitute that. So our equation becomes, dm doesn't look like a D, so let's dm m1 bar dx2. So this is negative plus m2 dx2. Next, we divide the equation by dx2, and that would give us, what's happening? And that would give us dm over dx2 dx2 equal to, so I'm going to swap my m to the positive 1 minus m1. Okay? So it looks similar with our equation right here, but our equation that we're deriving right now is in terms of dx2. Okay, dx2. Next, so recall that by summability equation, recall, recall that m, okay, is x1, m1, okay, plus x2, m2 bar. Okay. which means if we isolate M2 on one side of the equation, it gives us over x2, right? So we substitute this expression for M2 in our equation for dm over dx2. So let's substitute the expression for, oops, m1 over x2 minus m1. Okay. Next, we multiply everything. Okay, we multiply everything by x2. So multiply this by x2. That would give us dm over dx2 x2. And the denominator will go away. Minus x2 over times m1 bar. So we try to remove we take out m1 from the two expressions, but this one is equal to 1. Okay? So therefore, our equation becomes x2 dm over dx2 equal to m minus m1 bar. Isolating m on one side of the equation, we have m1 bar plus x2 dm dx2. Okay, so now that we have this general equation in terms of dx2 and x2, um, we can now try to use, this is now useful uh, for this graph, okay, because this is in terms of x2. So since we're talking about molar volume, let's replace m by v, which is the property we're interested in. So v equal to v1 x2 dv over dx2. Okay, so just simply replace m with v. And this equation actually looks like an equation of a line, okay, wherein this is the slope, okay, and this is the y-intercept, okay. So this is when we plot v versus x2, it gives us this line wherein v1 sub bar is the y-intercept, okay, and this is the slope. So in fact, we can use this equation by drawing a tangent line on the curve, okay, and taking the value of the y-intercept. So if we want to get the partial molar volume, we simply need to get the y-intercept. Okay, so um, since this is the equation of the line at x2, okay, let me copy paste that. Hold on. Okay, I copy pasted the diagram or the data of molar volume versus x2. So if we want to get the y-intercept, which corresponds to our partial molar volume, okay, we simply need to draw a tangent line to where x is at. Okay, so say x2. So say we're interested when x2 equal 2.7. Okay, so that means x1 is zero point 0.3. So we draw a tangent line to x2, and reading of the y-intercept, reading of the y-axis to get the y-intercept would give us the partial molar property for um, species 1, okay, on uh, the left side of the graph, okay? So this would give us, the y-intercept would give us v1 sub bar. On the other hand, the other side of the graph where x2 equal to 1, this would give us the partial property, okay, for species uh, 2. Okay. So this is how we get the partial molar property graphically. So using this equation, we know that this would give us, okay, the slope at this uh, so this line is represented by this equation, and the y-intercept is represented by the partial molar volume, okay, at partial molar volume species 1, and the other side would give the partial molar volume of species 2. So when we read that, it would give us. Let's try to solve the problem, which tells us that the chloroform or species 1 is 10%. So that means chloroform x1 is 0.1 and x2 is 1 minus that value, which means x2 is 0.9. So we draw a tangent line. Let's just modify this one so that it's tangent to uh, 0.9. Okay, so it's beyond the graph. Let me find another graph. Wait, hold on. Okay, I have not found in another graph, but let's just estimate. Okay, so should be tangent at x2 equal to 0.9 somewhere right here. Okay, so graphically, it seems that our V1, okay, is, if this is 750, it's about 500. Okay, so 750, and this is about the same distance as this one. So approximately, so from the graph, V1 is approximately 500 cm cube per mole, and V2 is approximately, so that's approximately the middle of 1 250 and 1 5. So let's get the average of that divided by, so it's about 1375. All right, we move on to the next required from us, the pure species. Okay, the pure species. How do we get that? Okay, so by the way, before we proceed, this method is called the tangent intercept method. Okay, so let's move that V1 right here and V2 right here. This is the tangent intercept method. So now that we're done with letter A, that's letter A. For letter B, how do we read from the graph the pure species molar volumes? Right, so it's actually simply just the uh, edges of this line. Okay, so that would give us, since remember this line represents the volume of the solution, so naturally when x2 is 0, so that means x1 is 1. At this point where x2 is 0, it means pure, the species 1 is pure, so that the uh, the behavior or the volume, the property of species 1 is equal to that of its pure species volume or property. Okay? The same way, when x2 equal to 1, that means its property for the molar volume is equal to its its pure species. Okay, that should be 2 property. I guess so. I'm referring right here to this point right here. Let me move this a bit downward so I can move this a bit. Oops. This one, just move that a bit right there. So the edges of the curve would give you the pure species property. Again, when x is 0, that means V1 is its pure species molar volume, and when x is 1 means this point right here is the pure species uh 2 molar volume. Okay, so uh try to read that. So if it's between 17, approximately between 1750 and 2000, 2000 plus 1750 divided by 2. So that's approximately, but somehow below that middle point right here. So let's just approximate it to 1/8. 1/8 cm cube per mole. Well, V2, let's approximate from the graph. It's actually near the partial molar volume. Okay, so that's about 2/3 of this. So 250 divided by 3 times 2 plus, okay, plus 1 to 50. So that's about 1,400. Right? Approximately 1,400 cm cube per mole. And finally, we're being asked for the infinite dilution. Infinite dilution, how do we read that from the graph? Okay, let's see how to read it from the graph. So we're being asked for the partial molar volume at infinite dilution, V1 bar at infinite dilution, and V2 bar at infinite dilution. So when we say infinite dilution, again, x here approaches um, x1, for species 1, x1 approaches 0. So we're in for this one, x1 approaches 0. Okay, so approaches 0. What we need to do, just like our step for um, letter A, okay, we need to draw a tangent line at 0. Okay, so it looks like something like this. Okay, so it it represents the line where the tangent line touches the point where x1 is 0. So that's the point x2 equal to 1. Right? So this line is tangent to x2 equal to 1. We try to read off from the graph, but it's quite difficult because it's outside the the graph, right? The grid. We try to just approximate 1, 2, 3. So that's so approximately 250. So this is 500, uh, 500, 250. So approximately um a very low value. Okay, so hmm. 750. So this is about 500 to 50. So let's write. Let me just check something. Okay, so that's approximately uh 250. So V1 bar infinite is approximately 250 cm cube per mole. Okay. How about the other uh species 2? The same way, we're going to draw a tangent line. Let me copy paste that here. Going to tangent line. Okay. At infinite dilution, so that means when we infinitely dilute x2, that means the point is x1 equal to 1 or x2 equal to 0. So that is this point, x2 equal to 0. Uh, it's difficult to read just like before. So approximately, let's just approximate it to 1,750. Okay, let me find another graph. Hold on. Okay, this is a better graph. This one shows the partial molar volume at infinite dilution of species 1. So this is the answer. So that's about, yeah, 250 cm cube per moles. So let's try to draw a tangent. Oops, not that. Let's draw a tangent. Okay. 2x1. So it's approximately, it's below, it's below 0. So let's just write infinite dilution. Actually, I'm not sure how to read this. It's beyond the graph. So let's just put a very low value, approximately V2. It is approximately, let's just put 10. Okay. So I need to check that the answer. I'll get back to you, but that's how you do it graphically. That's how you read the values graphically. All right. So this ends the solution for this example. All right. We'll continue the next lecture in the next video.